It is a pleasure to have Professor Yael Roichman as today's speaker in our webinar series on statistical physics. Yael finished her master's in materials engineering in 1997 from Technion in Haifa, Israel. She is right now working at Tel Aviv University, where she is affiliated with both School of Chemistry and School of Physics. She finished her PhD from Technion also in 2004, and from 2004 to 8 she was working as a research assistant in New York University. And in 2008 she has joined Tel Aviv University in her present position. She is an expert in the field of experimental soft matter. In particular, her group has made very useful contribution using the technique of holographic optical trapping and also single particle tracking. And she works in the general field of interface of biophysics, soft matter, and non-equilibrium statistical mechanics. So, although her earlier title was the equation of state of randomly driven colloids, I see there is a slight change in the title. So, with that, I would like to invite Yael for delivering the lecture. Thank you. And also another thing, anybody can ask questions anytime during the talk. Just raise your hand and unmute your microphone and ask questions. Thank you. Over to you, Yael.
Thank you. So it's a pleasure to give the seminar, and please interrupt me. It actually helps me tell the story. Yeah, so I changed a little bit the title because maybe my original title was a little bit overstating what I have, but I hope to reach something very to get closer to a state function, function and state equation for colloidal particles. So let me start by telling you the dream. Since I was an undergrad, and I believe many other people would have this idea that the framework of statistical mechanics is really like magic. And we would really much like to extend it to non-equilibrium statistical mechanics. But the way to do it is not clear. It's not clear what becomes of temperature. Is it a function instead of a constant? What becomes of the distribution, the Boltzmann distribution of the state? Is it a functional of a function of a temperature, or how to do this? And but I hope one day to be able to fill in the blanks here. So what I want to do in order to do this is what an experimentalist does, which is to measure things and to look at experimental systems and obtain phenomenological information in order to then advance the theory. So in order to do this, to gain insight into non-equilibrium statistical mechanics, the idea is to study not just one system, but as many systems as I can that are out of equilibrium, and then look for something that is universal to all of them, look for emerging phenomena. Specifically here in this talk, I will focus on coupling between fluctuations and driving in a steady state, and I'll explain later a little bit more. So first of all, a little bit of the background. So we look at colloidal particles. These are, in my case, 1.5 micron silica spheres. These are beads that are diffusing in water. This is what you can see here. And we track them, each one of them separately. This system is fantastic for non-equilibrium statistical mechanics because colloidal particles can be observed on the single particle level at the same time as you look at a cluster or a system full of them. And then we can really look at the underlying statistics of all the processes. Like we see here in the trajectories, the random walk. The equation that describes colloidal particles is the Langevin equation.
Yael,
yes.
We are not able to see the slide transition. We are still stuck on the first slide.
Really?
Yes. Now it is changing. Yes. Now it is on the 5th slide.
But we don't see the full screen mode. I think if you share your full desktop, it will be better. because we don't see the presentation mode. Yeah.
Okay, so I am going to do this. So let's see. Is this working now?
Yes, it's coming.
Yes, yes, perfect. Yeah.
Yes, perfect.
So that was the motivation, and here's the movie. So now you can see the movie.
Yes.
Cool. So these are 1.5 micron silica particles, and we're observing them. And actually, I'm drawing here the random walk that each one of them is doing, and you can appreciate the statistics or the different statistics of each of the particles. And so we describe them by the Langevin equation, and it turns out that there have been an infinite amount of experiments that have proven that colloidal particles can indeed be treated and explained, their motion can be explained using the Langevin equation, where you have basically the mass times the force is equal to the drag force, which is proportional to the velocity. This is and then you have these random thermal motions, and then you have some external force. So this is a friction, the random force, and the external force. And in a dilute suspension of colloids, we also know that it behaves really much like an ideal gas. You only have to exchange the pressure that you have in an ideal gas with the osmotic pressure of the colloidal particles. But then the osmotic pressure is just proportional to the density of colloidal particles times the temperature. And so this was our initial thought when we went through to do this experiment. We use holographic optical tweezers. This allows us to manipulate the particles and to actually push them out of thermal equilibrium. So what is an optical tweezer, and what is holographic optical tweezers? Well, an optical tweezer is just simply a very tightly focused laser beam. There are gradient forces that depend on the intensity of the beam, and thermal radiation or phase forces that are depending on the phase of the beam. And so if a dielectric particle, which is like a dipole, is sitting near an optical field, it will be drawn to the highest gradient point, which is in the focal plane. And then we can use both intensity and phase to manipulate the motion of the particles. This is, of course, very useful, and Arthur Ashkin got the Nobel Prize in 2018 for optical trapping, mainly for the applications in biology, but I guess the physics applications are as interesting. This gradient force actually depends on the refractive index of the particle and the refractive index of the medium, and specifically on the ratio. So if the refractive index of the particle is larger than that of the medium, you have attraction, and the bead is going to be drawn into the focal point of the trap of the laser. And this is where most people use optical tweezers. However, in many cases, it's useful also, and we will do it here, to take particles that have a lower refractive index than the media, and then we work in repulsion mode. And that means that the sign here changes and the particles are repelled from the laser beams. The amount of forces we can apply with optical tweezers is in the piconewton range, and we can manipulate particles any size from quantum dots of 5 nanometers to large cells of 50 microns. But in general, when we want to do very clean experiments, we usually work with between 0.5 to 3 microns dielectric particles. They could be glass or plastic. Holographic optical tweezers take this idea one step further. What we do is we take the beam, and instead of injecting it directly to the objective of a microscope, we pass it through a device which is called a spatial light modulator. This device can imprint a phase pattern on the light. And as you might be aware, an objective or a lens Fourier transforms the beam from one side to the other. So if we put a phase pattern in the back aperture of the objective by coupling the SLM to the back aperture of the objective, within the sample plane, we're going to get a Fourier transform of this phase pattern. And we know how to calculate the phase pattern so that we will get a pattern of many, many spots. So you use one laser tweezer, but you obtain many, many, many optical traps. And basically, the number of optical traps that you can achieve is very high. We usually don't work at that very high numbers. I think the most I used ever is 300 traps. But still, without any other optical elements, getting 300 traps from one laser is really nice. The second thing that is really cool about this device is it's computer coupled. It basically acts like a second screen. So you can project your phase pattern to this screen, and this is what will appear here. Only you can now calculate by computer the holograms that you want, these phase patterns, and change them while you are in the middle of an experiment. So this will allow you to change the position of a trap while the particles during experiment. So what you're seeing here is something that we're going to do later. We're projecting a set of traps and then replacing it with another set. So the transparent traps are the previous set, and the opaque traps are the new set. And you can see that particles that were drawn first to these traps are now drawn to the other set of traps, or particles that were repelled from these beams are now repelled from these beams. And so we can manipulate the particles by just moving the laser beams slightly so that the particles still feel them. So if we go back to non-equilibrium statistical physics, if we have on one range equilibrium where we have these particles diffusing in a fluid, we know the probability distribution and we know which states functions to use. We can
Yael, I have a question. Do you see the ballistic motion, or do you see it's overdamped?
No.
Essentially?
It's highly overdamped. The ballistic motion in colloidal particles you will start seeing effect of inertias if you go below a microsecond, so part of a microsecond. And we usually film in milliseconds. So for us, everything is highly overdamped.
Okay. Thank you.
But good question. So this is equilibrium. The second thing that we can do, we can, for instance, use optical vortex. This is a beam that focuses to a ring, and each photon on this ring carries angular momentum. So if you now trap particles on this ring, they will rotate. And this will induce something that is really hard to see here, and I'll be happy to tell you in another time. This will induce fluctuations in these beats that you would see if you were sitting on the co-rotating frame. So what you have here is, but when you analyze it all the way, you find out that you have some slow deterministic motion that you can calculate from hydrodynamic interactions without any thermal noise, superimposed with thermal noise, thermal fluctuations. But there's a complete timescale separation between the thermal fluctuations and the driving. And this has to do because the water molecules bump into these beads at a rate of maybe every once in 10 to the 14 seconds, minus 14 seconds. But the velocity of my particles is around 10 microns per second. So for the colloids or for the water always equilibrates much faster than the colloid is moving. So there's a huge decoupling between fluctuations and slow deterministic motion. And so when I found this out or realized it at some point, it was very frustrating for me, because if you want to do statistical mechanics, it's true that it's easier to calculate things if you know that the fluctuations remain thermal, but then you're not really going all the way to systems that are far in equilibrium. And so I wanted to figure out a way to use tweezers and colloids, but couple the fluctuations and the driving. And so this is sort of the reason why I went into this topic. So can you indeed couple these two timescales? And we thought of 3 different ways to do it. So the first way we thought of how to do it was to make a system that had a feedback to what is going on within the system. So if a particle is diffusing and I'm monitoring it and applying a feedback, then I depend on the fluctuations, and then this driving scheme will be on the time scale of the fluctuations, and this would make it a couple and interesting. So one such example is an information engine that we realized, where you have a particle flowing towards a set of traps that is like a wall. And this is in repulsion mode. So the particle is repelled from the wall, and then it remains diffusing near the wall. And then once in a while, if we observe the particle going upstream, we move the wall closer without actually touching the particle. And if you repeat this many times, you have converted this information of the fact that the particle is no longer near the wall to work, because you're pushing the particle against flow. And so this looks like this. Here is my particle. In green, you see the position of the laser light. And in blue, you see the trajectory of the particle. And you can see that we sometimes, if we can move the wall, then we can do it sometimes really fast in a consecutive motion. And sometimes we really, really need to wait. And so in this way, we're actually doing an information engine or a Maxwell daemon in order to push this particle against the flow about 3 microns. What I'm going to do now is release the wall in a second, and then you will be able to see or compare the flow rate of the fluid. So right now you're seeing the particle being dragged by the flow, and you can have a feeling of how slow we had to let the particle move in order to realize such an information engine. A second way is what I'm going to tell you today about, is to create additional fluctuations in the system, which are slow, as slow as any driving. And then we could look at a particle that is fluctuating, but you can see that once in a while it has this large motion, which is a response to an optical trap. And then finally, what we can do is we can drive the particle within water, but also another colloidal suspension. Now this second colloidal suspension can be thought of as a second fluid, in this case, a compressible fluid. And then many new phenomena arise, because there's what happens when the coupling is not so perfect. So you have perfect thermalization with the water, but the colloidal fluid is responding slowly to the driving that you put. And so this is a whole new set of experiments. And as I said, today I'm going to tell you about the athermal fluctuations. So that was motivation and tools. Now let me say a little bit about the effective temperature. So I don't know, but probably you all have the same feeling that I had when I started this project, that the effective temperature has been proven to work in very specific cases, and in others it doesn't. And it really depends which temperature you use, which definition of temperature you use in systems out of equilibrium. And therefore, it's not clear that it's interesting to define this effective temperature. As I said, it could be a function maybe or something else. Why would we define a scalar as an effective temperature? Nevertheless, we decided to study the effective temperature in this system. And the definition that we chose to use is the one that goes with the fluctuation dissipation theorem. Basically, it says that the response that you have in a system is coupled to the autocorrelation. So the response to a change from state 1 to state 2 is equal to the correlation in state 2 in steady state with a prefactor, which is the temperature. And this is true in equilibrium. And in an equilibrium, non-equilibrium steady state, you would just replace the temperature with an effective temperature. And basically what we wanted to know is, does this effective temperature, the fact that you can define it was done before. And I'll show you now a few examples. But does it have predictive power? Can it tell me what's going to happen in my system? So this is a beautiful experiment by the group of Felix Ritot, where they took a particle and they just switched its position between two states. And you can see one steady state and then the other steady state. So this is applying a force on the particle. And from this, they could do two things. Well, maybe I should define two timescales. There's a switching timescale and there's a relaxation timescale, where the switching timescale is when I turned on and off the perturbation, and the relaxation timescale is from the second I turned off the perturbation, how long does it take me to reach the new steady state? So these are two interesting timescales. And then what you can do is you can plot, in the case where the relaxation time is much smaller than the switching rate, you can plot the response is a function of the autocorrelation divided by the temperature. And wherever you have a linear relation, basically you get a well-defined effective temperature. And you can see that in that system, they could prove that there is an effective, it is possible to define an effective temperature. So, and when this condition doesn't hold, then they couldn't define an effective temperature. So not only is the effective temperature defined, as I showed you here, by this ratio between the autocorrelation and the response, but also you need to make sure that it responds on a long, on an interval of times. And then you know that your fluctuation theorem holds and that you can use this effective temperature. This is a very general way to write the fluctuation dissipation theorem. For colloidal suspension in steady state, you can use Einstein relation that is just one version of the fluctuation dissipation relation, and that tells you that the diffusion coefficient, which is the fluctuations or the autocorrelation of a position, with the mobility, which is the response to a force. So this now is an average fluctuation dissipation relation, because there's the diffusion coefficient is an asymptotic value as well as the mobility, and therefore I get a simpler relation. And so I'm going to assume that this is true in my system. So as I said, our aim was to see, to look at the predictability, or the state variable value, if you want, of the effective temperature. And the way we plan to do it is to implement a driving mechanism that seems like thermal noise, only slower, and that we can tailor or play with. And also, we'd like to look in a many-body system where hydrodynamic interactions exist. This is more interesting than just doing a simulation, a simple model. And the second thing is that we want to, I'm reiterating, we want to introduce fluctuations that are on the same time scale as the driving, so not very fast. And so they're not white noise. This is the difference between them and temperature. So let me tell you how we designed the experiment. So first of all, we take our sample, which is full of colloidal particles, and we split it in a virtual way, not really, but we assign for every particle in the suspension a virtual pixel in which it belongs. And within this pixel, we send a trap in a random location. So say I chose this pixel or this area that belongs to this specific particle, and I projected an optical trap. Now, at constant frequency, which I choose, this is a parameter of the system. Oh, this is the force that acts on a particle as a function of a distance from the trap. Yes, but so say that I turned on this laser beam, so a particle is starting to diffuse and it is getting drawn to this beam. Now I switch the optical plane, so I have another random position within this pixel, but it's a different position. And so now the particle that arrived here is drawn to this trap. Again, when it's farther from the trap, it's drawn with a weaker force, and the force it increases as it comes closer to the laser beam. And so this is how it looks. And you can really now try to see if you can observe when the beams were switched. So I hope you saw that from now and again, you have an abrupt motion, which tells you that the beam was switched. The reason we do this protocol of dividing the area into pixels is because we want the trap array to be random but uniform, because this somehow mimics temperature, which is uniform everywhere. So we did these experiments both in attraction and repulsion mode. So for attraction mode, it's easy. You just turn the lasers and project, random arrays of beams, and this is your experiment basically, and the beads are being drawn to all of these arrays of light. However, for repulsion mode, in the end, the beads are going to run away from your field of view. So what we had to do is project a square that confines particles within this region, and then project random traps in the middle. So if you watch this movie, you can see how the square remains constant more or less, but within the square, the traps are moving. Of course, now the traps are slightly less powerful, but this is an experimental constraint because you have the same laser power, but you need to divide it now to much more traps than you had in attraction. So now what we're switching or changing our parameter of choice is the frequency in which you replace the random array of traps. These are these two experiments you can think of as this toy where you have these holes and these balls, and then whenever a particle, a metal ball comes close to this hole, then it will be trapped. And this is like the trapping attraction regime. The repulsion regime is more like a pinball machine, where whenever you come close to a trap, you get kicked. And if you look at trajectories as a function of frequency, you see that if you change very slowly the position of the traps, then in the attraction regime, particles will become trapped within the trap and remain there in the trapped regime. And then when we switch the position of the trap, it will be free to diffuse again to a different location until the trap is turned on. So here it's diffusing, the trap is turned on and it's drawn back to this trap, and so on and so forth. But if you switch the traps really, really fast, you cannot see any trapping events, and what you see is something that is very similar to free diffusion. In fact, if you go much higher than 20 Hertz, which is impossible experimentally but possible with simulations, you get the particles experience a flat potential and they just diffuse normally.
So for attraction, will I get higher effective temperature because you have higher mean square displacement? Looks like when I compare the case of repulsion.
Yes. So when the highest temperature that we reach with attraction is higher than that of the repulsion. For two reasons. One is that the laser power is really not as strong, and the other one is because of the mechanism.
So can I say like this by looking at it, because I can calculate the mean square displacement of the particle, and it is much more in case of attraction. Just looking at the trajectory.
Yes, it's exactly right, and I'll do it in a second.
Thank you.
In repulsion, what you have is that the particles don't come close to any trap. So basically, it's confined to an area which is in between the traps. And so when I don't change the trap a lot, the trap's position, it remains in some small area that is free from optical forces. As I switch the traps faster and faster, it's less confined. And you can see here that it's diffusing almost as much as this particle. Of course, when I reach infinite frequency, it's a flat potential and it will diffuse exactly the same as anything. So if you had to guess how the temperature would look, you would say this is below room temperature and this is room temperature, and so probably it's going the average temperature or the diffusion coefficient or the mean square displacement is going to increase as I increase the frequency.
I have a
with
question.
Attraction, yes.
Yeah, I have a question. I would expect that when you are doing it very fast, then there should not be much difference between attractive or repulsive mode, but your trajectories in the far end of the frequency spectrum that do not reflect that somehow.
You're exactly right, because here the highest frequency I use is 20 Hertz. This is the highest I could experimentally, but and it's not very high. But if you do the simulations and you go to much higher frequencies, then these come together and end up as being the room temperature.
Okay, thanks.
So you could expect that the temperature goes, especially if you say that these trapped particles are 0 temperature, you could expect that at very low, so I would have very low temperatures and then increase up to room temperature. This is what you might expect. This is what I expected originally. However, what we see is slightly different. So let me just reiterate that so we have our experimental range is from 0.1 hertz. Slower than that doesn't make any sense. We can do it, of course, up to 20 hertz, which means that the time that we switch between the traps is from once in 10 seconds to 0.05 seconds. So we have here a range of switching times, which is interesting, and we can actually compare between the switching time and the relaxation time of the system and look if we see something when we are in conditions where the fluctuation dissipation theorem doesn't hold. Okay, so let me explain a little bit or show you a little bit in more detail what we see in attraction. And the reason I want to do this is that when you look at this trajectory, it's clear that this is not normal diffusion. And if some of you are familiar with anomalous diffusion, then you would say, okay, how do you know that this is even, like, how could you apply a diffusion coefficient to a system like this? And because our switching times are constant, the time a particle is trapped has a cutoff, which is the switching time. So if you look at long enough trajectories, at short trajectories, you see a step distribution which is not Gaussian. You actually see exponential tails. But when you look at long enough times, this whole distribution becomes Gaussian again, and you can look at this as if it's a normal diffusion. This is, which is what we need. This is in the harshest conditions. Usually it diffuses very close to normal diffusion in all the range. To make sure that this is indeed the case, you can look at the non-Gaussian parameter and see that for both attraction and repulsion, even though the direction is a little bit different, as you go to higher frequencies, this becomes very, or long time scales, this becomes very, very normal, like normal diffusion. And here again, I'm showing you the mean square displacement. Okay, so we want to calculate the temperature. As you said very correctly, we need to calculate the mean square displacement, use the Einstein relation, and extract from this the temperature. So this is the MSDs of all these different experiments that I had in attraction and repulsion mode. The long range MSD always looks linear, so we can extract the diffusion coefficient. And if we divide by diffusion for coefficient of room, free particles, then you can see both in simulation and experiments that we don't exactly get what we expected. We get an increase in the diffusion coefficient and then a decrease towards room temperature. So we start at room temperature. For the system that has attraction, we even start a little below room temperature. And then we go up and go back down. And so this was a surprise at the first moment, but then you realize, of course, that this diffusion has to do with how much you move. And
so, hi, Yael.
Yes.
This is Punabrata. So I missed it. What is D? I mean, you normalize D by D naught.
D naught is the diffusion coefficient of a free particle.
I see. Okay, thanks.
Right. So we put fluctuations or forces in random forces in the system. You could expect them to increase the temperature. So if you start with something that is, but on the other hand, if you put really, really fast frequencies, we expect to go back to room temperature. So maybe we should get an increase as we introduce activity into the system, and then a decrease when the particle is not able to follow it. So the peak here would probably be something like the time it takes a particle to diffuse from the previous trap position to the next trap position. So if you're really, really slow, you stay trapped most of the time, and only when the switching occurs, you are free to move. As you increase,
Yael, I
yes.
have a question. So you have a case where your Van Hove is non-Gaussian and your MSD is linear in time. Is it the case? It is just like diffusing diffusivity or some sort of.
No. So it's
No, it's not like that.
No. So maybe I should go back here. So in most cases, if you look at long times, this is diffusion, normal diffusion.
Yes.
You would expect a deviation from normal diffusion in these cases where you see these trapping events.
Yes. Yes.
But even they don't cause anomalous diffusion because the trapping times are fixed, are limited, are cut off.
Okay.
So as long as you look at times that are much larger than the trapping time, which is the switching time of the traps, you're fine. You're in normal diffusion.
Yes.
And this is why, this is why here in the edge, in the beginning, there are differences, but in the end, in the long time, everything looks linear.
Yeah. Okay. Okay.
Okay, good. So what I'm trying to describe here is why is there even a maximum? And the answer is that there is something like stochastic resonance. So like a resonance, because when if I would have switched the traps exactly at the average time it takes a particle to diffuse from one trap to another or to be deflected from one beam to another, the particle will all the time be in motion due to the forces, the optical forces. So that would be the most active it would be. And this is the maximum that we see. But if we switch too slow, so the particle reached its optimal position, then it's not moving. So it moves less. And if we switch too fast, it never has the time to go very far. So it is less active. So to optimize the motion of the particle as response to the forces, there is some specific frequency that would be optimal. And it depends on the intensity of the lasers, on the switching rate, on the density of the colloids, and so on and so forth. But it's non-monotonous, this diffusion coefficient. Okay, a second thing that we need to worry if we want to work with the fluctuation dissipation equation is that the mobility is not really changed, or is it really changed by the optical traps? And if you do this, you see that if you, in this case where the trapping is switched very, very, very slowly, we indeed see some effect on the mobility of the particle. The velocity decreases when the particle goes through an array of optical traps. But in every other, in higher frequencies or in repulsion, we see no difference. So the mobility changes, mostly doesn't change. But now we know how the mobility changes. We know how the diffusion coefficient changes. This is how the mobility changes for attraction and repulsion. So you can see in repulsion barely, and in attraction only in very small frequencies. So now we can really calculate the effective temperature of the system. So it's the diffusion, the mobility divided by the diffusion coefficient divided by the mobility, and then normalized by, when I say room, I mean without any optical traps. So it's the temperature of a free particle. And you can see both in simulations and in experiments that when we do this, we get a peak in the effective temperature, both in attraction and repulsion. Attraction is slightly more complex because of the trapping. So we are going to focus on repulsion in most of the talk. But you can basically see an increase in temperature and then a decrease towards room temperature. And as you stated before, we are not there yet. We haven't reached the state where the particle is diffusing as if the traps were not there. But you can simulate all the way there. Okay, so that was the first result, and that was interesting because now when we look at this, we had the following idea. Okay, so this is a trapping, this is a almost free diffusion. But if I look at this point, the effective temperature is the same here and here. But it's the same effective temperature with a different driving frequency. So the underlying microscopic behavior is different. Here, the particle moves, gets trapped, moves, gets trapped. And here the particle is just moving, but doesn't really reach anything. It doesn't reach the area of strong force with a strong attraction force. So we have a chance to compare two systems in the same effective temperature, but with different underlying microscopic behavior. This happens for the attraction. For the repulsion, we can do the same. And again, we can find conditions here is not as, at least in experiment, is not as robust, but in simulation it was. You can get two temperatures that are the same with different driving frequencies. And so we thought of this experiment. Let's check.
I have a question.
Yes.
A question. Can you please go back to 2 slides back? Yes. So what is the reason for this initial drop?
This has to do with the way we defined the diffusion coefficient and the mobility. Because you have there are particles that are most of the time trapped, a mobility will give you a finite value, but the diffusion coefficient would be as if this particle is trapped to and not moving at all. So it gives a sort of funny behavior. So this is the region where attraction, this region where really things don't really work nicely. It's not really a good model if you are most of the time trapped.
Okay, thanks.
But because of this, we said it's not as natural as a temperature because you never get trapped in a thermal force. And so this is why we moved to do most of our stuff in repulsion. Okay, so we have the possibility now to ask what is influencing the behavior of a suspension. Is it the effective temperature or the frequency or the underlying microscopic behavior? So what we want to do is we want to have a half of a system being in one temperature and one frequent driving frequency. The other half of the system experience a different temperature done by a different driving frequency. And now if these colloidal particles are ideal gas, then that difference in temperature will cause a difference in pressure. And these particles should move, to equalize the mechanical pressure between the two sides. So you expect that in the end, we will find that the density in one side divided by the density in the other side is just the temperature in the second side divided by the temperature in the first side. So we set up to do these experiments exactly because we can control with the traps the different temperatures in the half of the system. And so if we have a higher temperature in one side than the other side, we expect particles to go from the high temperature to the low temperature because of the pressure. But the question is, if the temperature are equal and the driving frequencies are different, will we see or not see particle flow? If particle flow is controlled by the effective temperature, then it doesn't matter what is the underlying microscopics. But if they are affected by the underlying macroscopics, then it doesn't matter that the temperatures are equal. So having defined an effective temperature cannot predict in which direction will the particles flow. So that was a question. And so now I'm going to show you a fact, something that we measured and proved, and then tell you why it's wrong. So here we start with a hot system and a cold system. And this is the movie that you're seeing here. The hot area is at the top, the cold area is in the bottom, and this movie is sped up. And if you wait enough, you will see that most of the particles are sitting now in the cold position, in the cold half of the system. So let me just go back to the beginning. So this is uniform. And then as we wait, you can see the particles are slowly diffusing towards the bottom part. Of course, not all the particles are going to the bottom part. We expect the density to be related to the pressure difference. And so you see, this is working. So in the case where the frequencies were equal, so the temperatures were equal, you can see what is the probability to be in the top side, in the hot side, and you can see that it's really half. So if the frequencies are equal in both sides, we don't see any motion, and that makes sense because the underlying microscopics is the same and the effective temperature is the same. However, if the frequencies are different, but also the temperatures are different, we see the particles, we see the number of particles in the hot region, and this is the movie that you've seen, decrease until it reaches some steady state. So particles do flow from hot to cold as we expected. And so in a way, we have proven in repulsion mode that the effective temperature has predictive powers. And we were very happy about this until, okay, then we had to do the second thing, which is to have different microscopic dynamics, but the same effective temperature. And so this is what we've done here. And you can see that in both cases, with the same frequency or with different frequencies, particles don't migrate. So this really does prove that the effective temperature doesn't depend on the microscope, or the predictive power of the effective temperature doesn't depend on the microscopic dynamics. So here is what we set up to prove, and you could write a state function now that tells you that or you could tune the effective temperature and define the effective temperature as a state variable. But as I said, this is not the whole story. Because the effective temperature is not what we tried to do is to plot the ratio of the density as a function of the ratios of the temperature, and it wasn't exactly clear if our results are following this or not. It was ambiguous. So then we went to look at active systems, active colloidal suspensions, and what is known about them. And it turns out that in active colloidal suspensions, when you go from osmotic regular pressure, so you go from osmotic pressure at equilibrium to osmotic pressure plus a mechanical pressure that is a result of the activity of the colloids, of the active motion, their velocity. And the temperature goes from room temperature to effective temperature. So actually, what I should be asking is what is the equation of state of these systems. I need to take into account the pressure as well as the effective temperature that is changing. I need to take into account the mechanical pressure. And if I look at active systems, then by Brady, it was calculated that the pressure is a regular osmotic pressure plus this mechanical pressure that is related to the friction coefficient and the velocity of the particles and the time the particles are diffusing, the persistent length of their motion. In my case, the force that I am applying results in a velocity through the friction coefficient, and I can write it in my conditions as the regular pressure plus some contribution that depends on the force that the particles are feeling on average, the time they move on average, divided by the friction. So I need my effective temperature, if you want, is something that I can calculate in another way also. I could calculate the autocorrelation of the forces, plug that into the equation of the mean square displacement, get an active diffusion coefficient. Again, this must depend on the forces, on the switching time, and on the friction coefficient. And from this, I can define an effective temperature. Since I know the friction coefficient and I know the diffusion coefficient, I can define a delta T or some other a measure of the effective temperature that depends on all these parameters. Now, this is an estimation because I'm estimating, I should say here, for active particles, their velocity, their speed is always constant. The direction is not, but the speed is constant. For my system, the force acting on the particle changes as a function of distance from the trap. So this is some averaging that I've done here. Also, my particles are not moving all the time. They're moving only if part of the time of the switching. So if I put here the switching rate or the switching time, it's an estimation of how much time they really moved ballistically, because if they're very far from the trap or the bead, they won't move. But as an average, this should work. And so my effective temperature should look like this. And so if I now take the temperature, the difference in effective the difference from the effective temperature to the regular temperature, and rescale everything by the switching time, which is like 1 over the frequency, then I should get all my experiments, all my conditions to fall on a straight line with a slope of 2. And this way I can relate or prove that I can relate the effective temperature to 2 things. One is the microscopic dynamics, the speed of switching, and the other thing is the average force acting on the particles, which is related to some effective potential that the particles are feeling. And when you do this, when you take all experiments and simulations and plot them in these conditions, so in simulations, it's clearer. So I'm going to show you the resultant simulation. All the curves in a simulation that doesn't take into account hydrodynamic interactions fall on more or less on one curve. All the simulations with hydrodynamic interactions, they fall on one curve for very high frequencies. For low frequencies, things change. And the slope without hydrodynamic interaction that should have been 1/2 is actually 0.8, and the slope with hydrodynamic interactions is even higher. So what we learn here is that, first of all, there is a connection. The effective temperature does have 2 contributions that we need to take into account, which is the time scale, the frequency, or the microscopic dynamics, and the effective potential, the active force. And that hydrodynamic interactions enhance this effect, and that my averaging here was a bit crude because I didn't get the right number. But the idea is there. So having said all this, it's clear that when we said that we have a similar effective temperature and different microscopic dynamics, we didn't look at all at what happens at the average force that a particle is feeling. And it could be that this is what is creating the changes, especially since we saw that it comes in both into the effective temperature and to the pressure of an active system. And so it should come into play in the system of driven systems. They are driven, they're not active, but it's very similar. So let's measure the average force. So this was hard in experiment. We moved to simulation, and what we did is we just measure the average force that a particle feels in every time of the simulation for different driving frequencies, and you can see that it changes, but then saturates more or less. And this saturation happens when the traps are moving so fast that the particle doesn't really have time to sample more than its near location in forces, so at the average distance from a trap before it even managed to move. And now what we would want to do is to see what's more important, the effective temperature or the active force. So we are going to do 2 experiments. We take the sample, we split it into 2 halves. We have one experiment in which the forces, the average forces of the hot and cold systems are almost equal, but the effective temperatures are different. And what we measure, this is the blue plot, we measure that the density doesn't change. Particles don't flow from one side to the other. Whereas if we take a very big difference in the active force, the average active force in the 2 systems, but the effective temperature is held constant, we see particle flow. So our conclusion is that, okay, now we managed to break the timescale separation and look at the coupling between these optical fluctuations and the driving of the system. We found that different dynamics can lead to the same effective temperature, but the effective potential, the average force that a particle feels, and not the activity, the microscopic dynamics of the system, is what controls particle flow. And so we believe that this is basically the mechanical pressure that is causing all of the motion, and that you could understand effective temperatures from the point of view of this active force, of the average potential that it creates. And with this, I'd like to thank you and the funding agencies and the student, NIRGO, for collaborating, the students who took part in this project. And as always, there are always open positions in the lab.
Thank you, Yael, for this wonderful talk. And any questions from anyone? Please raise your hand rather than asking all at once. Punnabrata, please go ahead.
Hi, yeah, this is Punyabrata.
Hi.
Yeah, yeah. So I don't think I understood everything, but but I wanted to understand a particular thing. So at in one slide, you showed that you assume that diffusivity, the relationship between diffusivity and mobility, right?
Mm-hmm.
Could you please go to that slide? I think a bit earlier.
Yeah, let me.
I mean, where you actually define effective temperature.
So the first time I defined effective temperature.
Yeah, right. Just after that, maybe, yeah, right, right.
Mhm.
I mean, what is this relation about? This kBT times mobility equal to D, the diffusivity, right?
Mhm.
But I mean, even in equilibrium, this has a limited validity. I mean, if you replace T, I mean, in equilibrium, T will be the T effective and T is same. But since I mean your particles are interacting, so then there will be a compressibility factor come into play, right? I mean, the usual Einstein relation I'm talking about.
Yeah, well, I'm working in dilute conditions, so I don't expect there will be okay. I should.
Well, I mean that could be the. I mean, see the next slide when you show us the these particle trajectories,
Mm-hmm.
and we do see that when the particles are actually repulsive, they are caged, and this might be due to this higher compressibility. I mean, since particles are repulsive and the compressibility is higher, so
Well,
they would not
so maybe
wander longer. I mean, they would not wander further.
so the
I mean, that
particles are
effect
not
also is there.
the particles are not repulsive. The particles are regular particles. The beams that I'm projecting are repulsive. So the forces that I'm giving are repulsive. The impulses that I'm giving are repulsive, but the particles themselves are not repulsive.
Oh, I see. So you are saying you are still in the dilute limit.
Yes, I'm still in the dilute limit all the
Oh,
time.
I see. Oh, I see. Okay, okay. Thanks for the clarification. Yeah.
Any other question? Okay, I have a question. Here throughout you have considered when you change the position of the traps at random. Okay,
Mm-hmm.
I was wondering that suppose you give them some dynamics. The positions are not changing at random, but following some dynamical rule, the positions are being changed, which could be particularly interesting because there is a lot of work on these particles advected by some potential, suppose in the field of turbulence or stuff like that. So I was wondering that if it could be, I mean, what happens when you have different effective temperatures? And then, yeah, can you comment on that? If
So you're asking what would happen if I had specific driving dynamics, not random, and then I had two effective temperatures.
yes, I mean, you do have some time evolution equation for the potential as well. Then I think, I mean, particles will try to, maybe after you have done it few times, after you have gone through few cycles, maybe some kind of a, I don't know. I mean,
So my
I can,
guess is,
yes, please.
yeah, my best guess today about these systems, which I told you only one of them, is that what controls really everything once you follow the system slow enough is mechanics. Okay, if you disregard the thermal fluctuations, you have mechanics plus thermal fluctuations. And so if you can calculate mechanically what's going to happen, this is what is going to happen. So if you can calculate mechanically, like Brady did, the pressure, then you know what is going to happen. What is controlling here, I haven't proven this. So when I said that I want to have a state equation, is that we know the effective temperature in this relation, and we know the pressure. We should be able to measure them independently, and get a complete state equation. But basically, everything is controlled by this average force that you're feeling, and the switching frequency, the dynamics. So if you have this interesting potential that is moving, it's still going to be a potential. You still can calculate the forces. You have an average force. You have an average time it acts. You have the persistence if you want. Then you can calculate or estimate what is going to happen.
Okay, thanks. And also, sorry, another short question. All these cases where you had shown, for example, this present slide where you have F1, F2, two different frequencies in two different zones. I think these work perfectly when they are on either side of the peak, right? For example, F1 is to the left of the peak, F2 is to the right of the peak. You don't get an issue because of that, right?
No. We try to work specifically on the two sides of the peak, but we also, you cannot have the same frequency at one side of the peak. You have to the same effective temperature at one side.
Yes.
But we did work with systems where the frequency was and temperature were on one side or the other. It's just that when you want to have different frequencies and equal temperatures, you have to be in two sides.
Right. Yes. Any other question?
Hi, I have a question. Am I audible?
Yes, go ahead. Please go ahead.
So here you showed that the mobility is monotonic, right? It's not non-monotonic.
Yeah, the mobility is not completely. It's not monotonic. Yeah. Here it is.
It's monotonic. Yeah. Why? Because is it due to the fact that the traps are moving? If the traps are, if the obstacles are static, and if we consider, suppose, a driven walker rather, then there is an average force, and then when the walker actually collides with the obstacle, and as we go on increasing the driving, so the current will be reduced there. There is a non-monotonicity is there. In the response.
Yeah. So the idea here was to take something and drag it through, apply a force and drag it through an obstacle, a moving obstacle array. But even if this is static, like this, almost static, 0.1 hertz, first of all, you see that when you cross near a trap, it changes your velocity. And also, the mobility depends on the force you're dragging. And we worked, what I showed you are forces that are related, dragging forces that are related to the experimental value of forces. But I think it's still monotonic because you average over the entire trajectory, not just.
Okay.
Not just if you're near one trap or far away from the trap.
I see. Okay. Thanks.
Any other question? Yes, Anirban, go ahead. Anirban, go ahead. No, we cannot hear you. Anirban, we cannot hear you.
Can you hear me now?
Yes.
We'll look at the duration sheet near the last slide. So to find out, for me, it's that we study in the Carnot cycle, the amount of energy and the temperature. And you are also that you assume the value plus minute so is there any limit to the kind of relationship beyond the temperature that you mentioned is valid or something like that? Or is it valid to any kind of density?
sorry, I couldn't understand what you're saying.
No, we cannot hear you. Please, your
Can you hear me now?
no. Yes, Anirban, we could not hear anything. Please type your question in the chat box. Meanwhile, do we have any other question? Yes, so he's typing his question. Yael, can you read it off or should I read it
Yes,
out?
I'm reading. In your last slides, you show me some relationship among the density and the T effective. Is it valid for any density and T effective? I'm guessing that you are talking about this relation, so this relation is for ideal gas, so it's for passive colloids. And the question that we had is, do we see this? So if I take one experiment where the density changes when I have this steady state density, does it relate exactly to the temperature? And it was not conclusive. We didn't have enough points, and we couldn't prove that it's wrong, and we couldn't prove that it's right. So this is work in progress in simulations, because in experiment, these are hard experiments, and it really is hard to get enough statistics of clean and comparable results. But I don't think it will hold, because I think that what controls everything is this this force. But yeah, stay tuned.
Okay, any other question from anybody? If not, let's thank Yael once more for this very nice and interesting talk. Thank you. Thanks a lot, Yael.
Thank you for inviting me. It was fun.
Bye.
Bye.